Hello everyone, I hope you're all doing well. So in today's video, we'll be going through the 2020 physics exam part 1, where we'll be going through short answer questions from question 1 to 10. Like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this video. Question 1. Two bar magnets are placed close to each other as shown in figure 1. Sketch the shape and the direction of at least 4 magnetic field lines between the two poles within the dashed border shown in figure 1. Alright, so we can see that there's a north and a south pole over here, and so they're going to be attracting. Like poles attract, opposite poles attract. So what's going to happen is, we know that field lines are always going to come from the north pole, goes towards the south pole, always. And that's nice and easy. We'll draw like 3 doing that. And we'll draw 3 curved ones like that. And still always the same, always from north. The field lines are always coming from the north pole to the south pole. And that's quite easily, that's it. That's what you just do for this question. Nice and easy. 2 marks, wow. Question 2. Gravitational magnetism and electricity can be explained using a field model. According to our understanding of physics and current experimental evidence, these three field types can be associated with only monopoles, only dipoles, or both monopoles and dipoles. In the table below, indicate whether each field type can be associated with only monopoles, only dipoles, or both monopoles and dipoles by ticking a tick in the appropriate box. Nice and easy. So gravitational, we know gravitational only attract. There are monopoles because they can only make one pole, which is like, you have a mass and they only attract. So in other words, they're just attracting and they're only one pole. They're only making one field. Like a pole means, mono means one pole. It's always just attracting. So overall, they are monopole, and that's the only thing they can do. So a monopole. Magnetism. Wow, man, let's look at magnetism. We know magnetism's like bar magnets. Let's have a look at a bar magnet. Is north and a south. So they always exist in pairs, which is a north and a south. So there are dipoles because there's 2 poles. Di means 2. Poles means they are, poles. And you cannot really create a monopole from it, because even if you break it, you will create 2 sections of, again, a north and a south. You cannot break a magnet and create a monopole. It's always going to be 2 poles, so it can only exist in only dipoles. Now let's have a look at electricity. Electricity can actually exist in both. Say you have a point charge, like a positive charge. A positive charge can be, of course, the electrical field lines are coming outwards, and so it can exist in both, like a monopole, and also it can exist as dipoles. If you have 2 poles, like positive and negative, these attract each other. Not just attract each other, they can exist as 2 poles overall. And so electricity can exist both monopoles and dipoles. Nice and easy. Beautiful. And that is it. Question 3. Electron microscopes use high-precision electron velocity selector consists of an electrical field E perpendicular to a magnetic field B. Electrons traveling at a required velocity V0 exit the aperture at point Y, while electrons traveling slower or faster than the required velocity V0 hit the aperture plate, as shown in figure 2. Alright. Show that the velocity of an electron that travels straight through the aperture to point Y is given by what? Okay, let's really understand what's happening here. So we have an electron which has, of course, a negative charge. And so it's moving into 2 things. So it's moving through an electrical field. So let's see what happens. If you move an electron in an electrical field, which, the positives are on top and the negatives are at the bottom, what's going to happen? Of course, the electron is going to experience an upwards electrical force because it gets attracted to those positives. It's a negative charge already, so it wants to get attracted to those positives. Also, those negatives will repel it to go to the positives. So we're going to actually produce an electrical force that's going to be upwards. And so it will look like this. So this force is electrical. I'm going to write E. And also there's going to be a magnetic force, because remember, you're going at a velocity, at some velocity, and you're in a magnetic field lines. You have magnetic fields. Yeah, you have a magnetic field. So there is going to be a magnetic force. And to know the direction, remember, you use your right hand slap rule. But because if it's an electron, you can actually use your left hand. Remember, using your right hand slap rule only works for positives. only works for positives. So you want to use actually your left hand. Using your left hand is so much easier. Use it for always electrons. So make sure your fingers are into the page, as you know, indicated by the field lines. Your thumb's going to go to the right because that's where the velocity is going to go. That's where the motion of the electron's going. And so your palm should be actually downwards. So my palm shows that it is downwards. So that's telling me that there's actually going to be a force. There's also going to be a magnetic force that's going to be downwards. I'm going to write FB, a magnetic force. So we have two forces that are going to be acting on it. And because we want to show that the velocity of an electron that travels through the aperture to point 1 is given by. So we wanted to go through aperture Y. To do that, we need to balance out these forces, because if we balance them out, the electron's just going to straight away go to Y. If these are unbalanced, it can go X or it can go to Y. It can go to Z. So if we wanted to go through aperture Y, we need to balance these forces. To do that, we need to make them equal. So we know that the electrical force, which is always given by Q times E, and the magnetic force, which is force B, is equal to QVB. If we want them to pretty much be to go to aperture, we need to make sure they are equal. So force has to be equal to your force of B, your magnetic force. And so let's do that. Putting that all together, so it'll be QE equals QVB. So you can see that those Q's actually cancel out. And so we're left out with E equals VB. And so your velocity is just electrical field strength over your B. And we've shown it through this. Done. That's it. Beautiful. Calculate the magnitude of the velocity V naught of an electron that travels straight through the aperture to point Y if the electrical field strength is that and your magnetic field strength is that. Beautiful. We know the formula, so you just sub in those values. So your electrical field strength is 500 times 10 to the power of 3. Make sure it's volts per meter, not kilovolts. Divided by your magnetic field strength, which is 0.25. We want to two significant figures. That's the lowest, so it's going to be 500 times 10 to the power 3 divided by 0.25, and that gives me 2.0 times 10 to the power of, so 1, 2, 3, 4, 5, 6 times to the power. Yep, so that is the velocity that needs to travel to pass nicely through aperture Y. C. At which of the points X, Y, or Z in Figure 2 could the electrons traveling faster than V arrive? All right. So what we're saying is, say we increase velocity. Now, what we know from these formulas is what? We know that the electrical force is not related. It's independent on the velocity because it doesn't have velocity. It doesn't affect it. It only gets dependent on the charge and the electrical field strength. So your actual electrical force is just going to be constant. So it's still going to be the same. But have a look at the magnetic force here. It is actually dependent on velocity, as we've shown from this formula. So if you increase your velocity, you're increasing the magnetic force. So imagine now, this force over here is larger if you increase your velocity. So now it's force B. So what we have is now it's an unbalanced force, where the net force, overall, if you add these two up, we'll have a net force that's going to be acting downwards. That's where your net force is. What tells us that if the net force is downwards, it's going to be curving downwards towards Z. So your actual answer has to be Z, because now it's an unbalanced force where, of course, your magnetic force is larger than your electrical force. And yeah, so let's write a nice statement here, a very detailed statement. So let's say magnetic force on a moving charge is given by force equals QVB, and so that depends on velocity. With higher speed resulting in a stronger magnetic force downwards. So we know that also the electrical force remains constant as it's independent on velocity, and also act upwards. And lastly, we just say the net force results in a downward direction due to a stronger magnetic force surpassing the electrical force. The electrical force. Hence, particle will arrive at Z. That's it. It's kind of very detailed, and it is a lot, but I hope that kind of, shows you what a nice answer looks like. It's not, the best. You want to write in dot points. You don't want to write too much like what I've done here. But yeah, this is very detailed in showing you why it goes to Z. And I hope it helps. Question 4. Let's have a look at this question. Let's use a different color. The Ionospheric Connection Explorer icon space with a satellite constructed to study Earth's ionosphere was launched in October 2019. Icon will study the link between space weather and the Earth's weather at its orbital altitude of 600 kilometers above the Earth's surface. Assume the Icon's orbit is in a circular orbit. Use the radius of the Earth as that. Alright, calculate the orbital radius of the Icon satellite. Nice and easy question. So, let's just draw a diagram. Be careful, because they said altitude, you need to look at this. So, you have this, and you have your... Say we have the Earth, and we have the... We have the satellite. Now, we're actually given the altitude above the Earth's surface. So, it's the distance between the center of your Icon satellite and the surface of the Earth. That. But remember, if we want the orbital radius, which, remember, orbital radius is the distance between the center of both masses. So you do need to include the radius. You need to add the altitude with the radius of the Earth to get the orbital radius. So that's going to be 6.37. Let me write it nicely. Times 10 to the power 6 plus 600 times 10 to the power of 3. Let's do that. So 6.37 plus 6 plus 600 times 10 to the power 3. That gives me, how many significance to 3? So 6.97 times 10 to the power of 1, 2, 3, 4, 5, 6. 6 meters. Beautiful. Question B, calculate the orbital period of the Icon satellite. Correct the 3 significant figures. Show you're working out. Nice and easy. This is an application of Kepler's law. So we know that period. Make sure you write this formula down. It's always, when you want to calculate period, it's normally always Kepler's law. So Kepler's law states, this is the formula. It's 4 pi squared r to the power 3, where radius, that r value is the orbital radius, over gm. So let's put that all into our thing here. So 4 pi squared, so r would be 6.97 times 10 to the power 6 to the power 3, all being divided by 6.67 times 10 to the negative 11 times your mass of the Earth, which will be in, it's not really given here, but it's in your formula sheet, in the VCE formula sheet, which is, if I'm not mistaken, was it 5.98 times 10 to the power of 24. And that is it. So putting this in your calculator, we should get 4 squared times 6.97 times 10 to the power 6 to the power 3, 6.67 times 10 to the negative 11, 5.98 times 10 to the power of 24. So that gives me how many significance? To 3 significance. So 5.79 times 10 to the power of 3. 1, 2, 3. Yep, 3. Beautiful. C. Explain how the Icon satellite maintains a stable orbit, circular orbit, without the use of proportional engines. What a nice question. I think this question has kind of been used in those old exams. If you haven't done those old exams from VCA, I think below 2015, you would see this kind of question a lot. And it really is quite easy to answer. But a lot of students might not understand what to give like the examiners to get the full marks. And I'm going to show you what you just need to answer. So let's just draw Earth here. Let me just show you what it is. And say Earth, and this is your satellite. Why does it, why do the Icon satellite maintain a circular orbit without the use of proportional engine? This is why. There's only one force that's acting on this satellite, and that is the force of gravity. And this force of gravity is always in constant in magnitude. So its magnitude is always the same as it orbits around the Earth. So a stable orbit means the radius is just always the same. It's like a nice blah, but let me just draw it quick like that. All right. And you also need to remember that it has a velocity that is perpendicular to the force. So a velocity that is perpendicular. And this velocity is in constant magnitude. So its speed is constant, but the velocity changes over time. So if without even the use of propulsion engines, the thing is going to move by itself because there's no work being done. There's actually no work being done by the force of gravity. So all you need to answer is pretty much to get full marks. This is what you just need to answer. You just need to say the satellite only experiences the force of gravity. There's only one force, that acts on it, which is just the force of gravity, which remains constant in magnitude and is always perpendicular to the velocity. And we also know that no work is done by gravity on the satellite, and so the satellite moves in constant speed and hence maintains this stable or circular orbit. In other words that I would tell students to think about it is think of it like when you look at, say, a high velocity particle and charged particle, and it moves through a magnetic field. Let's think about, not actually a magnetic field, let's think of another way. Think of it like, say you're a student, you're holding a, let's just draw a nice example here. Say you're a student in the middle, and so you have a rope. So you have this rope here. And so you have a little ball, and you're turning it around. You're rotating so fast that it's moving around in an orbit. So think of you're the center of mass, which is like you're the Earth, and so this here is your satellite. Now tell us what forces are going to be acting. Well, we know there's going to be a tension force that's going to be towards you. And there's also going to be a velocity that's always going to be acting perpendicular to that tension force. Think of it the same. If you maintain that velocity, if you maintain that constant velocity, what's going to happen? The thing is going to move at a stable radius. It's going to move at the same radius for all the time. And if you just keep doing that, and that's why it kind of maintains that, stable circular orbit without the use of propulsion engines. Because if you use propulsion engines, you're putting work, and so it moves at a higher velocity, which, it does so much work. But yeah, without the use of, propulsion engines, all we need to know is that the velocity is constant. So the velocity is, the speed is constant, and so that is why it maintains that stable orbit. So this is what you just need to pretty much answer to get actually those 2 marks. All right, so all you need to pretty much answer is the satellite. So the satellite experiences only a force of gravity which is constant in magnitude and is perpendicular to the satellite velocity. No work is done by gravity on the satellite, and the satellite moves at a constant speed and maintains stable orbit. stable orbit. I was going to explain it in terms of like, think of it like the questions that you normally get in exams is, there's one of the most kind of repeated questions is, say for example, you have, if I go up again, like this over here. If you have a high, let's say a charged particle and it moves through a magnetic field, just forget the electrical field, just this magnetic field. What happens, it curves in the nice radius and comes out. But if that, magnetic field was always the same. Imagine it was all around. It would move in a nice uniform circle and it will come back and it will just keep doing the same thing. It's just because why? It's because there's a magnetic force that's going to be acting on it always towards the center. And plus, you always, and the velocity is always perpendicular to it. And remember, it's always the same speed. The velocity has the same speed. And so this force also is in constant magnitude. And that's why, in other words, you can explain it like, that's why you need to state that what we just did there, that you need to talk about how it's in constant magnitude, that force, and it's perpendicular to the velocity, and hence, also the velocity is also constant. Just don't forget about that. And that's all you need to actually answer that question. All right, I hope that helps you out. Question D, let's really look at this part here. Figure 3 shows the strength of the gravitational field G as a function of orbital altitude h above the surface of the Earth. All right, so G, when this is the surface of the Earth, as you can see, when it's at the surface, we have 9.8, and of course they haven't drawn everything, so when you see this, it means it's still going on. So, all right, determine the changing gravitational potential energy of the icon star as it travels from the Earth's surface, so from 0 to the altitude of 600 kilometers, which is over here, above the Earth, and the mass of the icon satellite is this. Okay, first we need to calculate the area. Now, I think a lot of students might think this is just a triangle. No, think of it. This whole thing is like extended, but they haven't shown it. For example, if I'm drawing this nicely, think of it like this. It's an actual trapezium. Like that, and so like that. Something like that. Okay, so it looks like this if you kind of extend this part. And so think of this as 0, that 0 part here. That 600 is right over here, kilometers. And this part over here is 8.2. So this part over here is 8.2. And this part at the maximum point here is 9.8. So guess what? It's just a trapezium, because if you really look at the distance from here, that's 600 kilometers. This distance here, this part here, is just 8.2 from what we said. And this whole part over here is just 9.8. This whole big part over here. And that's all we need to actually calculate the area of a trapezium, because remember, the area of a trapezium is just half A plus B times your height. So your height is, of course, that. And this is your A, and that's your B. So putting that all in my formula, half A, which is 8.2, plus 9.8, times your height, which is 600, times 10 to the power 3, make sure it's in meters. And so that's going to give me my area. But be careful, this is a gravitational field strength versus distance. And so to get the actual energy, you need to multiply at the end by mass. The mass of the icon satellite in this case. So times, don't forget, 888, 288, and so that's going to give me my now energy. So putting this all in my calculator, 8.2 plus 0.8 times 600 times 10 to the power of 3 times 288. And that gives me, wow, it's a big number. So it gives me three significant figures. 156, yep. 156 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8, 9 joules. That's it. Beautiful. I think a lot of students will get confused because they might think it's like, they need to look at the units. Please have a look at the units. Be careful. They're telling you that it extends and they couldn't draw it. So that's why you have to draw it. You can also just find the area of this rectangle plus the area of a triangle. But I think just using the trapezium formula was much quicker because it just included both of them. Cool. question 5. Let's have a look at question 5. A rectangular wire loop with dimensions this is placed between two magnets that create uniform magnetic field strength of this. The loop is rotated with a frequency of 50 Hz in the direction shown in figure 4. The ends of the loops are connected to a split ring commutator to create a DC generator. The loop is initially in the position shown in figure 4. Be careful, they've used a split ring commutator in a generator. What does that do? So when you look at your oscilloscope, it's going to look like this. It's all going to be rectified. It's not going to move nicely. It's not going to move in terms of AC like that. It's all going to be rectified. Just be careful. Using a split ring commutator in a generator will rectify those voltages. And so the question says, in which direction, clockwise or anti-clockwise, will the induced current travel through the loop for the first quarter turn as seen from above? So this is an application of the Lenz's law, because of course we're going to induce a current as we rotate it. So let's think about it. So the field lines are going to pass through the plane, and they're not going to go inside that plane. So we start off initially with zero flux because they're not passing through the plane. But as you do a quarter turn, the plane will look like this then. And now look at this. The field lines are going to pass through it. So what has happened? There has been an increase in magnetic flux. There has been an increase in magnetic flux. And we know by Lenz's law that we try to oppose that magnetic flux. And how do we do that? You know that increase in magnetic flux? We want to try to decrease it. The way we will decrease it is by doing the opposite. So the magnetic field direction is there's going to be induced magnetic field direction in the opposite way, so this way. So now, to know the direction of the current, we use our right-hand grip rule and make sure your thumb is going to go to the direction of the magnetic fields, which is to the right. And so your hand should be kind of, I don't know how to describe it, but it should kind of look, if I draw the current should kind of be rotating like this. So let me rub these now. We don't need these things here. It should kind of be rotating like that. All right, should be kind of rotating in that. So if you kind of bring it back to the plane here, this is how it should look like. This is how the current would look like then. And so this, if you're looking at it above from the above, this is actually anti-clockwise. This here is anti-clockwise. Beautiful. Calculate the average EMF measured in the loop for the first quarter turn. Of course, we're going to generate an EMF because there's a change in flux. So EMF, like always, EMF is just your N times your change in flux, which is, remember, it's just your area times your magnetic field strength divided by your change in time. So we don't need that negative, of course, because we're just trying to calculate the value, the magnitude of it. So let's do that. So your N is that, what is it, how many? It's just a rectangular wire, so it's just one. Your area is just going to be 0.050 times 0.035, and that's going to times by the magnetic field strength, which is just 0.2 times 10 to the negative 3. Make sure it's in Teslas, not milliteslas. And we're going to divide it by the time. But be careful. How do we get the time? We're given the frequency. This frequency is going to help us get the time. Because remember, to get period, it's just 1 over frequency. So 1 over 50, which is pretty much 1 over 50, is 0.02 seconds. So remember period. What defines period? Period is how long does it take for a full rotation. So fully rotating that loop. But we only want a quarter turn, so we have to just divide it by 4 pretty much. Which gives me, so dividing it by 4, that gives me the time that it takes for a quarter rotation, which is 0.005. Done. So putting this on my color, I should get my EMF that's going to be produced. So I get 7.0 times 10 to the power of, so 1, 2, 3, 4, 5. Negative 5. I just want to double check it. 1, 2, 3, 4, 5. Yes. So we we produce a 7, wow, it's a very low voltage, but yeah, a 7.0 times 10 to the negative 5 volts that we produce. Beautiful. Not any mistakes, looking good. C. On the axis provided below, sketch the output EMF versus time for the first 2 rotations, include and scale on the horizontal axis. Alright, so what I would do for this case is first I would draw the flux graph, the change in flux over time. And to do that, it's just going to be, let me draw a nice change in flux over time graph for 2 rotations. And that's going to help me draw the EMF graph nicely. So, alright, so change in flux over time. Alright, so we started initially with no flux because remember the magnetic field lines were not passing into the plane. So it started at 0, and of course for a full rotation it will look like this for 1 rotation. But because we're doing 2 rotations, it's going to look like that. Beautiful. So, and to draw the EMF, it's just pretty much whatever you see turning points, make sure these are going to be your x-intercepts. So if we have a turning point here, it's going to be here, here, and here. And so, can you see how this part here is positive? This gradient here is positive. It's going up. Think of your EMF. When you're drawing your EMF, it's going to be at the bottom. It's going to be negative. So you're going to be drawing at the bottom, like that. It's because, remember, there's normally a negative here. Don't forget about that. So it's going to look like this. And so now it's just going to look something like this. If I draw it nicely, like that. Pretty much that's what our EMF graph will look. But that's not true. That's not fully true because we're just going to rub this out now. And so this is how it should look overall. But of course, remember, a lot of students forget, this is only when you have slip rings. You have a split ring commutator which rectifies those negative voltages. So it will look like actually this. All those negative parts are going to be just reflected. Like that. Like that. That and like that. So we can rub that graph out. And so now we have this. That's how the actual graph looks like. So, yeah. So it looks like that. All right. So let's draw that nicely here. So it's going to start here. Move like that. Like that. I want to just make sure, how many do I do? So 1, 2, 3, 3 in the middle. Okay, so that. And like that. So we draw those, and beautiful. And we also wanted to include a scale only on the horizontal axis. So to do that, it's just halfway in between these. That's 1 period. It took 1 full rotation took how many seconds? 0.02 seconds. So that will be 0.02 seconds. This here will of course take 0.04 seconds, and here will be 0. And pretty much, I think that's all you need. You don't even need to go above and beyond. And so, yeah, and of course the EMF that's produced is, 7 times 10 to the negative 5, which we don't need to include here. But that's it. That's beautiful, yeah. Just be careful with the, we are using the split ring commutator, so it does rectify it. Let's have a look at D. Suggest 2 modifications that could be used to the apparatus in figure 4 that would increase the output EMF of the DC generator. Easy. If we want to increase that EMF or the voltage, it all depends on then just writing the formula. So your B times your area over change in time. We can, to increase your EMF, we can increase the number of loops, we can increase the magnetic field strength, we can increase the area of the loop, or we can decrease the time it takes. So we can actually increase the rate of the speed, and so that will decrease the time. These are so many ways you can actually increase your EMF. So you just need 2. So I would just say 2 of them, like increase the number of loops and increase the magnetic field strength. That should increase my EMF. Easy 2 marks. Increase the number of loops of wire. And the next thing, increase the magnetic field strength. All right. So now question 6. 2 physics students hold a coil of wire in a constant uniform magnetic field as shown in figure 5. A. The ends of the wire are connected to a sensitive ammeter. So ammeter measures the current, of course. The students then change the shape of the coil by pulling each side of the coil in the horizontal direction as shown in figure 5b. They notice a current register on the ammeter. Alright. And it makes sense. Of course, there's going to be, a current that's going to be registered because there's a change in flux. You've changed. There is a change in flux. Will the magnetic flux through the coil increase, decrease, or stay the same as the student changes the shape? Of course, it's going to decrease because remember, look at the area. You have a large area initially, and then you pull it and you make a little area. Remember your flux from the formula is your area times your magnetic field strength. If you increase the magnetic field strength, which we're not doing, we've just messed up with the area. We've decreased this area, so it decreases our magnetic flux. So decrease in that case. So B, explain using physics principles why the ammeter registers a current in the coil and determine the direction of the induced current. All right, like we said, of course the thing is gonna it's gonna register current because we have there is a change in magnetic flux. Remember here, we have pretty much, let's say, maximum flux. So we have some maximum flux here, and so we then decrease the flux. So there's now a change in flux. Remember, EMF, which is voltage, is only gets produced when there is a change in flux. And because there's now a change in flux, because we've decreased the flux in this case, there is a change in flux. There's going to be an EMF produced. And remember, EMF is just voltage. If there is a voltage produced, there is also going to be current that's going to be produced. And that's why to explain why that it is. And so also the next question, determine the direction of this induced current. So if we want to determine the direction of the induced current, we need to explain it by pretty much using Lenz's law. And that's what helps us, And so let's also explain how we would determine the direction of the current. To determine it is first by using Lenz's law is to see if the flux is increasing or decreasing. If we're initially going through this high flux and then we've decreased it, we have done a decrease in flux, a decrease in magnetic flux. So what Lenz's law states is it wants to oppose that change. It wants to increase that flux, and to increase it, let me explain it again. So this is what you want to really explain. So we know that the magnetic flux through the loop is decreasing. And so it's decreasing in the direction of into the page from what we see here. We want to also state, of course, the direction. So we know by Lenz's law that induced magnetic field will oppose that change in flux. That's what Lenz's law states. So it will still be directed into the page. Let me just draw a diagram for most of you that don't understand Lenz's law. So think of it like this. If you have a wire loop here, and say you had a magnet here, side of a magnet. This is your north and south. So your field lines are coming in like that into. And so let's say you're approaching it. You're putting the magnet into it. We are increasing the magnetic flux because now the field lines are passing inside of this coil. So the flux is increasing. If the flux increases, we want to oppose that change. How are we going to oppose that change? There will be induced magnetic field that will go in the opposite direction. It will be in the opposite direction. So we will use our right-hand grip rule in this case, and we will learn the direction of the field induced current. But it will be actually different if you were now decreasing it. For example, a lot of students forget, but if you pull that magnet out, what's going to happen? Again, what's happening is that you've decreasing your magnetic flux, and by Lenz's law, it wants to oppose that change. It's going to still put it in the same direction. Your induced magnetic field is still going to be in that same direction, because it wants to oppose it. And so, and that's why it's still in the same direction, because we've decreased in this case. We've decreased our flux, so your induced magnetic field is still into the page in this case. And so using your right-hand grip rule, and make sure your fingers are into the page, your thumbs into the page, you'll see that it's actually, your current should be directed clockwise. It should be directed clockwise direction. And so that really does explain why. That really explains. So we've learned that the induced current moves clockwise. And so let's write, so 3 marks, we're just going to explain what we just talked about overall. I'm so sorry, it's very hard to kind of explain, especially you need to really use a lot of examples. But that's how you would do this question. So a change in flux induces, we said, because we want to explain why the ammeter registers current, so it induces a voltage in the coil from this formula, which remember N, so magnetic flux over change in time, since there is a voltage produced, there must be current also produced. Current also produced. Done. And so to explain the other way, well, like the direction, we're going to use this Lenz's law. So the magnetic flux through the loop is decreasing, and in the direction decreasing into the page. So by Lenz's law, the induced magnetic field will oppose this change. Will oppose this change. So we'll oppose this change in flux, we want to say. So it will be directed into the page. So using the right hand grip rule, current flows. So your induced current flows, oh, my hands really hurt. Current flows clockwise overall. That's it. That really, I think, summarizes everything that we talked about. Beautiful. Next question, C. Let's have a look at C. The students then push each side of the coil together as shown in figure 6A. All right, so they're pushing it back so that the coil returns to its original shape as shown in figure 6B, and then changes to the shape in figure 6C. So we've gone from this initially, then we changed it back, then we a little bit pushed it again and back to this. And describe the direction of the induced current in the coil during these changes. Give your reasoning. Again, we just have to use, again, Lenz's law. So what we're saying is, like, if we're going from 6A to 6B, what will be the current direction? Easy. Again, use Lenz's law. So what's happening? We can see that there has been, when you're going from 1 to 2, from here to here, there is going to be an increase in flux because there is more area. And so remember, like what we said, if there's an increase in flux, it will try to, Lenz's law states that it will try to oppose this flux. So there's going to be an induced magnetic field that will be out the page. Will be out by remember, when there's an increase in flux, it's gonna oppose that change in it will be in the magnetic field will be in the opposite direction, so out the page. So using your right hand grip rule, make sure your thumb's out the page, and you see that your fingers actually your fingers are going to be rotating pretty much anti-clockwise, if I'm not mistaken. Yep, that looks good. Yep, anti-clockwise from my hands. It's going to be moving anti-clockwise. And so what about when you're going from 6B to 6C again? So you've gone to your original shape, and now you've decreased that again. So you've decreased your magnetic flux. Like we said, Lenz's law states that it will try to oppose that change, and it's still, when we decrease it, remember, the magnetic field, the induced magnetic field direction is still in the same direction when it's decreased. So imagine your hands into the page, and so it should be rotating clockwise when you're going from 6B to 6C. All right, so let's just write, 2 marks. Wow, we'll just really be kind of quick with this one. Where's it? 6C. All right. So going from figure 6A to 6B, there is an increase in magnetic flux. Hence, by Lenz's law, so Lenz's law, the induced current, so the induced current flows anti-clockwise from what we said. Yep, anti-clockwise. And we just, by the right hand grip rule. By the right hand grip rule. Done. So the same thing also for this one, going from figure 6b to 6c, there is a decrease in magnetic flux, hence by Lenz's law the induced current flows clockwise wow, I'm writing this too much, by right hand grip rule. You want to write it very short in this case, grip rule. And that's it. Beautiful. 7. Oh, let's have a look. I love electronics. This is nice. A rechargeable electrical toothbrush uses a transformer circuit as shown in figure 7. A secondary coil inside the toothbrush is connected through an iron cord to a primary cord that is connected to the mains power supply. The mains power supply is 240 volts RMS, and the toothbrush recharges at 12 volts RMS. The average power delivered by the transformer to the toothbrush is 0.9 watts. Assume that the transformer is ideal, so there's no power loss in this transformer. And this is actually kind of useful because I've actually always wondered, I have an electrical, toothbrush, and so, yeah, this is kind of great because I've never understood how they... Is it, is it Bluetooth or something? That had the way it recharges. And so this is how it recharges. It uses a transformer. Wow. And so it induces a current. Okay. So calculate the peak voltage in the secondary coil. So what I want to do is I want to summarize this whole thing into a basic circuit so I can really answer all the questions in seconds. So this is your 240 volts RMS. So 240 volts RMS, primary circuit is. And so we'll have of course, the transformer, and so then let's call this it's a globe, but let's call it the toothbrush. The recharging of the toothbrush, and we know it's 12 volts RMS here, and we also know that 0.9 watts are on both sides. Remember, because of the transformer, it's ideal. So this side's going to receive 0.9 watts, and this also is going to receive 0.9 watts. Both sides are just going to be receiving at the same power. So both this is going to be 0.9 watts, and also this is going to be receiving 0.9 watts overall. Calculate the peak voltage in the secondary coil. Easy. So we know in the secondary coils, it's 12 volts RMS, so we just want to convert it to peak voltage. So we know voltage peak is just square root of volts RMS. So we just need to multiply 12 volts by square root of 2. 12 times root 2. Root 2. It is 17 volts in two significant figures. Determine the ratio of the number of primary turns to the secondary turns. Easy. We know that the primary turns to the secondary turns is just the same as the voltage in the primary divided by the voltage in the secondary. So what's that voltage primary? We learned that our primary voltage is 240. And our secondary was 12. So it is 20 overall. 240 divided by 12. Yep, 20. E. Calculate the RMS current in the primary coil when the toothbrush is recharging. So show you're working out. So now we want to calculate the current in here. And that's easy. We have the power that this is, consuming, which is 0.9 watts, and the voltage. And so we know that power is just voltage times current. So if we want current, it's just power over voltage. And our power was 0.9 divided by the voltage in terms of RMS, which was 240. Is that right? Yes, it is. So what's 0.9 divided by 240? It's a very small number, but yeah. We want in milliamps, so I'm going to just times it by 1,000. So it's pretty much the two single figures, that's 3.8 milliamps. Done. Next question. Question 8. Figure 8 shows a small ball of mass 1.8 kilogram traveling in a horizontal circular path at a constant speed while it is suspended from a ceiling by a 0.75 long string. Alright, a nice question. Use label arrows to indicate in figure 8 the two physical forces acting on the ball. Okay, of course there are two physical forces. The force of gravity that's acting on this ball from the center of the mass. And of course there is going to be a tension force from the string. It's going to be acting here. So tension string. Of course, there's if not physical, there is a net force that's going to be, going this direction overall. But that's not what we need to label right now. just this. These are your two physical forces. Calculate the speed of the ball, show you're working out. Okay, so we know to calculate the speed of the ball, we want the net force. Because remember, if you calculate that net force, so your net force is this direction overall, which is mv squared over r. Can you see how it has v? And that's what we want. We want the velocity. That's what we need. So we need to calculate the net force. So what I'm going to do is I'm going to put these into a triangle. All those forces, I'm going to resolve them into a triangle. So I'm going to add this here, like that. These questions are mostly repeated in a native exam. If you do a lot of your NEEP exams, quite a lot of NEEP exams have this. And yeah, if you do a lot of PAS exams, this question is so much repeated in exams and easy to get full marks for if you play around these questions. So your force of gravity is, of course, we're going to put the force of gravity down here. That's your force of gravity. So your angle here is still 25 degrees. And then, of course, your net force is going to go this direction. So that's your F net. And, of course, Fg is what? It's just mass times. So your mass, what was our mass? 1.8 times 9.8. It's actually just 17.64 newtons. And so we want to calculate F net. So to calculate F net, this is our opposite and this is our adjacent. So we're going to have to use tan. So tan of 25 degrees is equal to your opposite, which is F net, divided by your 17.64. So overall, your F net is that times tan 25, which is just 8.22. I'm going to write the whole thing because I'm going to have to, I think I have to do something extra. 66709. Okay, so that's your F net. And remember, F net is just mv squared over r. Just don't forget about that. It's just the same as mv squared over r. And that's what we want. We want the velocity. We do have the mass, but what about the radius? Don't get confused. This here is not your radius. Let me just rub that out. I mean, we've already done that question. So this here is not your radius. Your radius is the radius over here. Circular path, this radius. So we're going to have to draw another triangle. Like that. Like that, another triangle. And so now, if I know that's 0.75 meters, and so this here is, of course, 25 degrees, I want the distance of x, which is your, in this case, r. So this is your opposite, and this is your hypotenuse. So I'm going to use sine in this case. So sine 25 degrees is equal to your opposite, which is r over 0.75. So your r value, your radius is just 0.75 sine 25 degrees. All right, so let's put that there. Well, it's a lot of work, but yes, it is. So all I have to do pretty much is velocity, just a little bit rearrange it. It's just going to be the square root of 8.22566709 times your radius, which was, we said, was 0.75 sine 25. That's your radius, divided by your mass, which was 1.8 kilograms, and then take the square root, which gives you velocity. That's it. Put in this. That's a lot of calculation. Wow, it is 4 marks, but I didn't expect this long. 0.75 sine 25 divided by 1.8. And that gives you 1.2 meters per second. That's it. Two significant figures. That's it. Yeah, 1.2. Wow, that's very long. And yeah, but that's good. It's a good question. Nice, easy. Just mostly trigonometry. Question 9. Let's do this. An ideal spring is compressed by 0.15 meters. A ball of mass 0.2 kilograms is placed in contact with the compressed spring. The spring then is released, causing the ball to move horizontally with a velocity v across a smooth surface as shown in figure 9. Smooth means there's no friction, which is great. If the spring constant is that, show that the magnitude of the initial velocity v of the ball is actually 12 meters per second. Corrected 2 significant figures show working out. All right. Well, because they told us that how much the spring is compressed, so let's really zoom into this. Let me just draw a diagram here. So initially the ball is here, and no, say that the spring, uncompressed, it's this length, like that. And so the ball's here. And so now they've kind of compressed it with the spring. So now imagine it's compressed. Now it's compressed at some distance like this. So the compression, they told us it was compressed by 0.15. And so if the ball is here and, you know, they're not letting it go. They're holding it. So we know that the velocity is 0 at this position here. So we know velocity, so your kinetic energy has to be 0. We're going to use energy conservation 100%. And so all that energy that's acting here is your spring potential energy, because you have compressed that spring. So it's going to be at its max. And so when, you know, you let it go, when the spring, you know, goes back to its normal strength, the ball's going to be let go. And so all of that spring, when it's at this position, all that spring energy is going to be now 0. It's all going to be converted to kinetic energy, which is max. And we know that the total energy overall is constant. So all we need to do is add this, and we must equate it to this, because they should be, the total energy of both of these should equal to each other, because it's constant. All right, so spring potential energy, which is half k times change in x squared must equal to half mv squared. So those halves can actually cancel out. We don't need these halves from both sides. So what's our k? Our k was 1250. Your change in x is how much it was compressed, which we said was 0.15 squared. It's equal to your mass. What's our mass of the ball? 0.2 times your velocity squared. So that's going to be just overall, bring this to this, divide this side by that, and then take the square root of that. That's going to give you your velocity overall. Done. So, so your velocity is just 1250, 0.15 divided by 0.2. So that gives me, so I didn't square it, sorry. Why did I not square that? Top part, square that. And I get 11, let me write it here. I get 11.858, which is, to two significant figures, 12 meters per second. So we have shown that it is, the initial velocity is 12 meters per second. Done. Calculate the speed of the ball after it had fallen a vertical distance of 2.5 meters straight looking out. All right, let's really look at this too. So we want to calculate the speed. All right. So when the ball, you know, goes flying off at that speed, it's going to now go through projectile motion. So it's going to go down here. Remember, this is 3 meters. So it'll probably be around here, where it's now gone to the distance of 2.5 meters. So say the ball's here now. Say the ball's here. How do we calculate the speed? You need to remember, to calculate the speed, you need to both make sure, this is your speed here, this direction. You need to break it down to its horizontal and vertical components. We know our horizontal component is going to be constant. And that constant value is what? We just calculated, which was, make sure it's 11.858. And what about the vertical velocity? To calculate the vertical velocity at that point, we need to actually use some SUVAC calculations. So we know initially that there is no vertical velocity here. It's only horizontal, so u equals 0. A equals negative 9.8, of course. Your S, your vertical displacement, is going to be, of course, negative, what we said, 2.5 meters. Okay, so it's going to be negative 2.5 meters. And we wanted to calculate the final velocity, your vertical final velocity. So the formula comes as v squared equals u squared plus 2as, where v is, of course, the square root of u squared, which is 0, 2a is negative 9.8, s is negative 2.5. So doing this, negative 2.5, it gives me 7 meters per second in terms of the vertical velocity. So now I have to just use Pythagoras theorem to calculate the velocity, the overall velocity. So to get the overall velocity, it's just the square root of both that 7 squared plus that 11.858 squared to get that velocity. that gives me 11.858 squared. And so overall, that gives me to two significant figures 14. So it's 13.76, but overall it's 14. And yeah, that looks good. So is this the last question? Wow, we've been going for a lot. Yeah, this is the last question. All right, question 10. Jacinta designs a computer simulation program as part of her practical investigation into the physics of vehicle collisions. She stimulates colliding a car of mass 1,200 moving at 10 meters per second into a stationary van of mass 2,200 kilograms. After the collision, the van moves to the right at 6.5 meters per second. This situation is shown here. All right. Calculate the speed of the car after the collision and indicate the direction it would be traveling in. Show you're working out. So we want to calculate the velocity of this car here after the collision. So we're just going to use, of course, conservation of momentum. So we just need to equate the momentum of, adding these momentum of these two cars, and it should be equal to your momentum of the final of these two cars. So it's just going to be pretty much mass of the car, so mass of the car times your initial velocity of your car plus your mass of your van times your initial velocity of your van, and it should be equal to your mass of your car, your final velocity of your car, plus the mass of the van and the final velocity of the van. So we know that the mass of the car initially was 1,200 and the initial velocity is 10. Oh yeah, be careful. Make sure to pick, when you're doing momentum questions, you make sure you pick a positive direction. So I'm going to take right as positive. So plus mass of the van, which is 2,200, and the velocity, it's 0. Initial velocity is 0. So this overall is just going to be 0. So we didn't need that. It's equal to your mass of your car again, so 1,200, and the velocity of the car, which we're trying to find. So your final velocity of the car after the collision, plus your mass of your van, times your velocity, which is 6.5 to the right, so it's positive. Great. So let's answer that. So what's that? Times 10. So that's going to be 1,200 equals 1,200 VC. So 2,200 times 6.5. 1,430. Okay, so your VC is just going to be 12,000 minus 14,300, all being divided by 1,200. That's going to give me your VC. That's going to give me, so that gives me overall negative 1.916. Now, be careful. A lot of things, negative. How are we getting negative? It's the direction. Your negative is your direction. It tells you that this car over here, after the collision, is going to go to the left at this velocity. So our velocity is just 1.9 to what? To two significant figures, which is just 1.9. And your direction is going to be on the left because it has negative. So it has a negative, so it's going to go to the left. Beautiful. Explain using appropriate physics why this collision represents an example of either elastic or inelastic collision. So to determine if it's an elastic or inelastic collisions, so for an elastic collision, let's talk about this. So for an elastic collision, the kinetic energy, the kinetic energy before must be equal to the kinetic energy of after the collision. So before the collision must equate to the after. So if there's no loss of kinetic energy, then it's an elastic collision. But if the kinetic energy before is not equal to the after, then it's called an inelastic collision. So let's find the kinetic energy before. So that's easy. It's just adding the kinetic energy of both masses. So half. What's the mass of the car first, which is 1,200. What's the velocity that was going? It was going at 10 meters per second. Plus half the mass of the van, which is 2,200, times the velocity, which was 0 squared. It wasn't moving. So overall, the final before velocity of overall the system is just overall 1,200 times squared. It's actually just 60,000 joules. Now let's find the kinetic energy after the collision. So it's just going to be the kinetic energy of the car after the collision. We found that the velocity was 1.9, around 1.9 squared. Plus, what about the kinetic energy of the van? So, what was the final velocity? It was 6.5 squared. You don't worry about like the negative, because when you square them, it will just make them positive anyway. 0.5, 200, 1.9 squared, plus 0.5, 2,200, 6.5 squared. So that gives me 48641 joules. These two are not equal to each other. So the kinetic energy before is not equal to the kinetic energy after. Hence this is an inelastic collision. Beautiful. One of the most typical questions you will get in exam. Whenever you do collision stuff, it's one of the most easiest way to get pretty much 3 marks. It's just doing this. Collisions, like is it elastic or inelastic? Question C. The collision between the car and the van takes 40 milliseconds. Whenever you're given the time, when you're talking about collisions, one of the formulas that should straight away come to your mind is that impulse is equal to a force change in time. That is the first thing that comes. Whenever you're talking about collisions and they give you the time, you should straight away remember this formula. Calculate the magnitude and indicate the direction of the average force on the van by the car. So we want the average force. We want to calculate this force here. So calculate the magnitude and indicate the direction of the average force on the van by the car. So it's on the van by the car. So when the car hits it, the car is gonna push on the van, which is gonna be a force on the right. This is the force. It's gonna be on the right. So we already know the direction is gonna be to the right, but we just need to find the average force. Easy. We just need to calculate that. So we just need the impulse overall. So remember your impulse, which is just your mass times your change in velocity. And so we know what is the mass of the, in this case, it's actually the van, because that's where the collision has happened to it. It's it's pretty much taking the force in. It's the van. It's 2,200. So 2,200. The final velocity of the van is what? So after the collision, which is 6.5. And it was initially at rest, so it's pretty much 6.5. So this will give me my impulse, which is 14300 kilograms per meter. So kilograms, meters per second. And so we got our impulse, and putting them in this formula, we get, what is our force? So force is just your impulse divided by your time, which is 40 milliseconds. Make sure it's in seconds, so times 10 to the negative 3. That's going to give me 2-second figures. I want to write it to 2-second figures. So 3.6 times 10 to the power of... Oh, make sure it's in kilonewtons. Oh, it's already in... So just divided by 1,000. It's just 3.6 times 10 to the power of 2 to the power of 2 kilonewtons. That's it. Next question. Calculate the magnitude and indicate the direction of the average force on the car by the van. So it's pretty much, the forces are going to be the same. So when the car gets hit, the van is going to produce also a force in the opposite direction, but it's going to have the same magnitude. This is just an application of Newton's third law. So overall, the with on the car by the van, so the van pushes on the car, yep, it's going to be the same force as we just calculated here. So 3.6 times 10 to the power of 2, but it's going to be, of course, in the opposite direction, left. And so to get actual full marks, do you want to state how you got that? So Newton's third law. The force is the same in magnitude, but in opposite direction. And that's it. I mean, you can do more calculations if you want. Like, for example, if you want to calculate that, also you can do the same as what we did. So the time's the same, and it's just doing all this calculation, but for the car. And it will be the same overall. But yeah, just apply Newton's third law, and it should be much easier and quick for yourself. And I hope you guys learned something from this video. Yeah, I hope you guys enjoyed this video. Please make sure to like and subscribe and share this video with friends to help them out a lot. I hope it helped you a lot, and make sure you guys take care of yourselves. Thank you so much and have a great day. Bye bye.